Okay, too many things to, okay, drop out. Okay, drop out. There's one parameter you need to specify, okay, for dropout, which is the probability. Probability. You need to specify 0.5 point. What probability? The probability you want to disable the node. Okay, the node you want to disable. For this case here, when I put a crosshair here, it means we drop this node. We assume this node does not exist. That the purpose is what? To prevent overfitting. What do I mean by overfitting? If I have a sample of two classes like this. Okay, if I have some sample like this, then this will be the good decision function, right? I can separate into a class 1 and class 2. But if you go for the overfit, if I have a sample right here, what does it mean by overfit? Then you will have your decision function like this so-called overfit. It can train almost 100% correct. But when you truly apply it, you will get into trouble. Why is that? Because if you have a test sample here, appearing this test sample is much closer to class 1 instead of class 2. You know what I'm saying? Okay, that's called overfit. So for some case, we drop out some of the node during the training that will prevent overfit. Now, it's not required, but usually dropout only apply to the fully connected layers, not the convolution layer. Everyone know what I'm saying? 也就是到最后2层，我们不是要 fully connected 吗 ？or dense layer， 我们只有在那个时候我们会去做 dropout。当然有人会在 convolution layer 做，可是看起来没有必要。Okay? Okay? So the dropout usually only apply to the fully connected, usually the last 2 or last 3 layers. Okay, that's it. Okay? Okay, let's go. But anyway, for the user, you need to specify what should be the probability you want to drop out. Okay? So it depends on your training sample and what should be the best probability so that you will prevent the overfit like this. Okay? So it mentioned here, okay, you only apply to the fully connected, which will be the last MLP layer. Okay? Batch normalization. Okay, here's the equation. Okay? Zi will be the sample in a batch. Okay, Zi will be the sample. Suppose we have a total of m samples in the batch. So we calculate the mean. We calculate the variance. Okay? The variance here. So this, as you know, in statistics, the normalization is called z-score, right? So we expect z-hat will follow standard normal distribution, right? You will see follow standard normal distribution. We'll put an epsilon here. It's nothing but just prevent divided by 0. That's it. Okay. So the numerator is it's 0 mean. Okay. Then we divide it by the standard deviation. But after that, then we output the value is given by gamma and beta here. Okay, as I mentioned, z hat will follow normal distribution, a standard normal distribution. then we should put expected the mean, okay, and plus the shift, okay, the scale and the shift. Now, the good thing for the user, gamma up and the beta are determined automatically. They are the parameter. You don't need to worry about what should be the gamma, what should be the beta. No, the only thing you need to determine is you want to use batch normalization or not. Okay, you don't have to use it, but if you want to use it, just go for it. Just go for the batch normalization. Okay, and these two scale and shift parameter will be determined automatically. Okay, and then this will be the output. This will be the output. Okay, after the batch normalization. Usually it will be better. Okay, especially for training. Okay, it will make the training faster. Okay, then we know about what is filter, and you know something about the pooling. Here's the padding, as I mentioned. Okay, for this example, this is the input image. If we use a 3x3 filter, right? We use 3x3 filter. Then after that, the output will becomes what? 4x4. Okay. Okay. So anyway, if you select padding, which means after that, we will fill the missing column and row with 0. This called zero padding. Zero padding. Okay. Well, actually, it does not have to be 0, but you can use the remaining information and take the average. But that's be fine, because if you have the input like this, when you go for the next convolution, then the 0 value will become something, right? 你不要把它领了，因为你后面还是要你到下一阶段你再做 convolution， 这个领可能就会被附近的字填掉了嘛，所以不用担心啊。Zero padding. If you use carrots, it just specify the padding equal to the same 一样，就表示你的尺寸不要去动它，它自己会去填领啊。Okay, they call padding. So in that case, I mean especially for a very deep CNN model, I mean the size will getting smaller and smaller. So, but in this case, you will maintain the original size. Okay, for the feature map. Okay, after the convolution. Okay, the other very important technique for CNN model training is data augmentation. Okay, especially when you don't have enough training sample, then you can use, for this example, suppose you only have a correct image like this, then you can rotate it by 90 degrees, so that you can, which means data augmentation allow you to create a dynamic environment. Okay, for example, the data I collect is only this handwritten digit line. However, when you can rotate it by 45 degrees, by 10 degrees or more, then you can create a more sample that will simulate the dynamic changes of the environment. But you must be very careful when you use data augmentation, especially for rotation. If you have an image like this, now suppose we rotate it by 45 degrees. What will happen for this image? When you change it by 45 degrees, you may have something. The output, nine will become, it will rotate 95 degrees, but you will get something. This is whole break. You know what I'm saying? Because we are talking about a digital image. Don't use it as the input. Because of what? Your CNN model might take this as the features. instead of technon. No, that's because you input the image like this. You will take this as the input. You know what I'm saying? So you must be very careful. So you want to rotate, you have a better to extract it from a larger image. So for this one, you can rotate the image. After rotation, you can still find a square, right? You know what I'm saying? Okay? When you go for the rotation, you should rotate the larger image and then find the small patch. That's the result. Okay. For shift, the same here. If you shift to the right, then you might have the image like this. Now you must be very careful because you might take this as the feature. You will identify it, okay, instead of the target, okay. So anyway, for augmentation, you can go for rotation, shift, the shading, scaling, okay, and blah blah blah. Okay, you can do. It won't hurt, except for you will extend your training time, but it will make your model robust. Okay, you can handle if you can training with all the dynamic environment, then you will have a better model when you deploy to the real application environment. Okay, that will be something good. Always use data augmentation. It won't hurt. Even it cannot improve anything, but it won't make your model worse. Okay, can only be better. Okay, so always think of it as a possible way to improve your model. Okay, I'll skip I'll talk about the recurrent neural network. Okay, because this algorithm cannot work with the parallel GPU. Okay, so variance gradient, we already mentioned that. Some of the problem is not very serious because after you take a lot of iterations of the gradient, it will become zero. Then you will get stuck. The other way around, in the opposite way, is the gradient will getting larger and larger. But it's okay because if this gradient value is too large, you can always set up a cap, right? You can set up a cap so that the value will be limited in a manageable range. So it's basically this is not a major problem, but this could be a problem, okay? Could be a problem, especially in the early day of deep learning, okay? Now, about the optimization, I made it very quickly. The first, basically, we have two choices, okay? If you have no idea, I mean, you can have many choices, but these are the two I would recommend it. The first one is called gradient descent. You already have done this gradient, but why you call stochastic gradient? Because for each training time, you will randomly pick up a sample. It's random. It's stochastic is randomly pick up a sample to train the model. Okay. But it does not have to be just one single sample. It can be a very, very small batch, okay? Randomly, you pick up randomly and train the model. So first, you can just go for the gradient descent, okay? But it's still very important to select the, I mean, this is just like the eta I just mentioned, learning rate, okay? Learning rate before, it's very important. The other one, which is highly recommended, called ADAM, okay? Called adaptive moment estimation, okay? Adaptive moment estimation. Basically, it's a gradient descent, but take a look. First, you calculate the gradient, okay? The gradient, and the power of the gradient, Now, then this is M, so this, you can call this the first momentum. and this will be the second momentum because theta squared. Now, how do you call this value? How do you call this equation? You learn that from the quality control. You learn something from quality control for SPC control. This is called what? When you set up the upper bound, lower bound, usually you will set up, especially for you guys from Taipei Tech. That's your advisors. What? Now, beta is nothing but a coefficient or weight called moving average, right? Now, this next step is previous step, moving average. So it updates the moving average based on the gradient. It updates the second moment, okay, based on another weight called beta 1 and beta 2, nothing else. That's it, okay? And then it do some normalization of M and V, okay? Here, based on the experiment, it do the normalization of the first moment, second moment, based on the beta, okay, beta 1 and beta 2, that's it. And then this the final equation, okay? Again, when you take the final equation here, it's nothing but the gradient descent. M is the gradient, but it's based on the moving average. The good thing about it is what? See that? It's adaptively change the learning rate by the variance here. Now you can think of eta here just an initial learning rate, but it will update the learning rate, okay, based on what? Based on the variance or standard deviation. That's it. So it's still a gradient descent, but the learning rate can be adapted, okay, can be adaptive changes, okay, by the moving average of the variance. That's it, okay. So it's highly recommended. You just go for the stochastic gradient or adder. Okay, that's good enough. Okay, here's some others choice. You can just take a look. But if you fail for both, then maybe you need to try something else. Okay, I mean, basically the value of the training won't because of the optimization, but a lot of based on the learning rate. Okay, the learning rate. It plays a very important role. Right here, it suggests the learning rate is 0.001, a very small learning rate, starting learning rate. Okay, here's some suggestion for beta 1 and beta 2. Okay, you can just follow the default value. Okay, default value. Okay, but with a very small learning rate. Okay. When I say small, not usually we don't mean 0.1. We mean 0.01 or 0.001. Okay. Okay, so that's it. And here the learning rate can be adapted. Okay, can be constant, can be as a function of the iteration, or it can be a time step based on the time step. Okay, which means what? Whenever delta t, if delta t means 10 iterations, then it will, for every 10 iterations, it will reduce the learning rate. So that's a lot of, this is highly recommended. As I mentioned, you can just run 100 iterations with a larger learning rate. When I say larger, I didn't say 1 or 2 or 10. Okay, I might say 0.1 or 0.01, but after that, you might reduce it to a very small learning rate. Okay, so here's give you the curve. This is a constant. Usually we go for a constant. This is a stepwise learning rate. Okay, for this case, it will reduce the learning rate for after for that previous example after 10 iterations, or it can be the exponential or simply as a linear function of the iteration number. Okay, so that's it. So if you have a good idea, just go for these steps. Okay, for every 100, for example, then you can see what's going on. Always print out this. Okay, loss function as okay. As I mentioned, the loss function could be a mean square error or the cross entropy. Okay, you have two choices. Okay, especially for classification, even for segmentation, image segmentation. Usually for image segmentation, we go for the mean square error, but you can think of segmentation as a pixel-wise classification, so that you can still use the entropy. Okay. Okay, I skipped the propagation. You can take a look at the example if you want to learn more detail, because I showed the procedures right here, how to do forward propagation and backward propagation. Okay, so that's it. Okay, so when you develop an CAN architecture, here's something you need to keep in mind. For convolution layer, you need to determine what should be the number of convolution layer. What should be the number of filter for each convolution layer? Okay. Should I use a very deep convolution layer and each layer with only a few filter? Or should I use a relatively shallow convolution layer, but for each layer I have use a lot of filters? Okay, so that's your choice, depends on your application again. Okay, and then you need to determine the filter size, should be 3x3 or 5x5, and the stripe. Should you move 1 pixel at a time or 2 pixels? I just recommend just 1 or 2. Don't even try to 3 or 5. Unless you have a very specific purpose. Should we go for padding? And what should be the activation function that you are going to use? If you have no idea, go just use red rule, except for the last layer. Okay. For the pooling, you may skip the pooling, but if you decide to use pooling, I just recommend just use the default, the pooling size 2x2. Okay. But you need to determine what should be the pooling type. Should be maxima and min, or the square root. Okay, and the stripe by default is 2. Okay, some people will use, after the convolution, you may go for max pooling and min pooling at the same time. You know what I'm saying? After the convolution, if this is the output feature map, then you go for max pooling and average pooling, and then do something later and combine them together, and then go for the next convolution. Some people will do the thing like that. Okay, so you need to determine you want to go for the batch normalization or not. And then for image, you need to do the flatten. Okay, flatten to convert two-dimensional image or two-dimensional feature map into one-dimensional feature vector. But if you are working with time series data, the flatten is not necessary because the input is already a one-dimensional symbol. Okay, then for the dense or the 40 connected layer, you need to determine what should be the number of the dense layer. I would suggest at least use 2. Okay, excluding the output layer, use 2. Okay, and mostly no more than 3, because you will consume a lot of decision variable here. Okay, because they are fully connected. Okay, and activation function. If for classification, the last layer should go for softmax. Okay, for regression, never use red root. Okay, then you need to determine what should be the probability for the dropout? As I mentioned, dropout only apply to the dense layers, okay? Now, for optimization, you need to determine what should be the loss function, mean square error, or cross entropy. What should be the optimization algorithm? Are you going to use either the SGD, okay, or other? Then the batch size. What should be the batch size? And what should be the number of iterations and learning rate? Okay, what should be the this could be the most important one. Okay, this could be the most important one, the learning rate. So you have a lot of choice. Okay, you have a lot of choice to determine. Okay, so let's say about the CNN. Here, quite a few very famous CNN model since the early development called .NET, developed by Netcom. Okay, the breakthrough is by is NSNet. Okay, in early almost 20 years ago, but the NVIDIA should thank the developer. X is the very first model that used GPU that and separate the model, the CM model, into two branches and work simultaneously. That is the very first one, thank God, to use the GPU. You know, the early day GPU is just for gaming, just for gaming. And after that, it create the AI company called NVIDIA. Okay, it's just thing. And after that, here's some very famous model, Google Net, especially VGG Net. Okay, VGG. Even as a developer in 2014, it's still very popular. As I mentioned, even something after 10 or 20 years, people still using it. It means it got to be very good. Okay, if you have no idea at all, just go for this as a baseline model. Okay, use it as a baseline model. For VGG Lab, it has a two versions. One is called VGG 16, the other one called VGG 19. And also, you can download the VGG pre-trained model. You have the pre-trained model with ImageNet. Okay, you know the ImageNet have more than 1 million image that contain 1,000 classes. Okay, the good thing, as I mentioned, when you train the CR model, you need to start with a random initial value for the filter. But if you go for the pre-trained model, which means you can use the trained filter as the initial solution, and then train your own sample. You know what I'm saying? Okay, that'd be good. That's called transfer learning. Transfer learning. You transfer what? Transfer something learned from ImageNet to your own data set. Okay, we call transfer. The only thing you need to do for transfer learning, you need only to change the last layer. For example, for ImageNet, the output layer will contain 1,000 nodes. But if you, for your application, you care only about normal sample and defect sample, then the output node will be only 2, just 2, normal, defect. The only thing you need to do it with pre-trained VGG, that's the only thing you need to do, okay? And the other very famous one is called residual net. A lot of up-to-date model is take residual net as the baseline model. Residual net is developed by He Kai-min. Okay, it's work for FB, very famous guy. Later on, we'll talk about Math RCN, also developed by He Kai-min. Okay. residual net. Also residual net has a lot of different versions. The deepest residual net contains 152 layers. 152. Okay, so deep. Okay, but so deep, it means so expensive to train in terms of the computation time. Okay, so it's up to you. Application. Okay, so let's say here's some up-to-date model. One is called convolution next. The other one is convolution mixer. Okay. Efficient net could be another thing you can take a look, because it will show you the rule or find the best, the number of layer, number of filter, okay, and even the input size, the input image size, that will give you the best result. Okay, the efficient net. Okay, I will finish all the remaining part next week, but let me talk about convolution next first, because for assignment 4 you need to use this one. This is the up-to-date model. Okay, this is the up-to-date model. Carlos will be here, but personally he doesn't like this because it involves too many parameters and relatively complicated to train. Okay, but anyway, I need to mention. Okay. Convolution next should be. I'll skip. I will go back to talk about the remaining models next week. Okay. Oh, here's convolution next. Okay. It performs better than the swing transformer. The transformer is better than transformer. Okay. So that what swing transformer use is applied to the convolution next, except for convolution next is based on the convolution. That's it. Okay. Now here's some major difference. Take a look here. The first, okay, it will repeat. This is so-called the block a lot. The residual lag it will go for a field convolution, and then the other one, this is called skip connection. Okay, skip connection. Then connect here. That's why it can go so deep. When you go deep, the gradient will vanish. But after every 2 or 3 convolution, the original input will bypass the convolution, and then it will add up to the output one more time, so that no matter how deep it goes, you'll be fine. Okay, the first for the convolution network, it used the model. It used the so-called invert bottleneck. Okay, usually the bottleneck, you will use the bottleneck like this. Okay, it's the bottleneck. The bottleneck here, we use 384, 96, 384. That's the bottleneck. I mean, the number here, it means what? The number of filters. The number of filters. But it used the inverse. It used the inverse bottleneck. It means what? In the middle, getting in the middle, called inverse. Okay, that's the first thing. The other thing about convolutional next, Carlos, give me a few more minutes. Okay, here's the example. Let's take a look at the example. This example show you we have a batch of 3 samples. We have 3 samples. That's 3 samples. 3个样本. But each sample has 4 features. So X1, X2, X3, and X4 are the features, not the sample. Okay, everyone follow me. So for batch normalization, you try to normalize. Okay, normalize the feature one for all samples. So we calculate the mean and the standard deviation, then we normalize it. Okay, that's called batch normalization. But for convolutional next, it go for the layer normalization. Okay, it go for the layer normalization. So for each sample, take a look here. For each sample, it calculates the mean and the standard deviation for all features by column. Everyone follow me? That's the difference here. Okay. That's called layer normalization. Okay. So batch normalization is the typical approach, okay, used by the CNN, but for the convolution next, or even for the swing transformer, it used the layer, okay, normalization, which means for each sample, it will take the mean and the standard deviation from all features, okay, from all features. That's called layer normalization. That's the only difference between batch normalization and layer normalization. And based on our experience, it could be better to handle the illumination changes, okay? Illumination changes, but you can try it out. Okay, but anyway, that's something new. But the baseline is still residual net, okay? So which means the training. It takes time, okay, for the training, okay? I will finish all the rest. So let me talk about the assignment number 4, okay? Again, the assignment is just like what you have in okay, this is a wafer die, a normal wafer die. This is a defective wafer die. Okay, and this is underexposed wafer die. Okay. Now the training. I asked you to just train the normal wafer die and the defect wafer die under the normal lighting. Okay, but for the test, you will see some highly underexposed, so that you can evaluate what's going on here. Okay, when the environment for the text image has been changed compared to the original training environment. Okay, so we just need to identify 2 classes: a normal or defective. That's it. Okay, so here you have a three question to answer. Now, first, Carlos will provide you a very concise or condensed Sierra model. Then you train the model from scratch. Okay, from scratch, from compare with the pre-trained. Okay, Carlos will provide you with some pre-trained VGG system and apply it to the same data set. Okay, and also you need to compare the result of the pre-trained VGG with the VGG that trained it from scratch. Okay, because the pre-trained VGG is based on the training of the image length. Okay, and you can see, is there any difference with the pre-trained model or not? And finally, the third model is just, again, is a pre-trained convolutional next, okay, for the classification. Especially, you can concentrate for the underexposed text sample, okay, and see what's going on here, okay? Then report the detection result by the confusion matrix, okay, by the confusion matrix, okay? False positive, false negative, okay? Then I make the comparison, okay? That's it, okay? We put the note here, you may try the class weight, okay? Because the training sample for the normal and the defective could be different, and you can see well the weighted loss function helped your detection or not. Okay, so that's it. Okay, that's for assignment number 4. Any question? Okay, Carlos, it's all yours. Okay. If that would be possible, if you can come earlier next week. If you have a question about your project, you can come to me, make a discussion. Okay. Otherwise, I will just write my comment on it. But if you do need a discussion in person, just come to me before 1 o'clock. Okay. Okay. Good. Okay, then see you next week.
Yeah.
Should I make it larger? Okay. So for this assignment, because the data set is not that small, I already put the data set in my Google Drive. So if you are going to use Google Colab, you need to just run this file, this line, so you can get it from my Google Drive. One of the advantages of using Google Colab, or disadvantages you may, that you can upload files here. But you know that uploading files is slower than downloading. That's why I decided to put it there, and you can just download it from here. Okay, but you can put any file here and access any file from the notebook. That is here, right? You just click in the folder, and that's it. You just have to make sure that it will go back to the. Sorry, this works. We go back in the directory. It has to be in the content. So that's the root folder for the notebook. How this I'm going to explain. Basically, you just run it, and then it will download and unzip the file. Here is, and then you just unzip it, and that's it. Now you can see the file. If you go here to the content, you can see here the data set, right? It was in there last time. Now you can open it, and you see the. So the tree goes like this. Is the root folder, and then we have a test train folders, and each one includes 2 folders for defective and for normal. So that's how it's. I think that's the way you should work when you are working with your data set, because it's easier to import. So now we just check that we can import it, and we have 2 folders inside it. Okay. So remember that before you start, you have to. I forgot to mention. You have to change the runtime. Now remember to select the GPU, right? Because otherwise you don't have a GPU. Now we can check which GPU we have. This NVIDIA SMI. So we have a Tesla T4 with 16 gigs of VRAM, which is quite powerful, I would say. You can see the usage here. 15.3 gigs. A lot. So that's the GPU that they give you for free, basically. So for this assignment, we are going to be using Keras as the as the front end or high end API, and the back end is TensorFlow. Most of the things we're working in Keras, I don't think we are going to go back down to TensorFlow because it's not that easy. For the confusion matrix, we are going to use scikit-learn. As I said, if you use Google Colab, you don't need to install absolutely anything because everything is already there. You just import the confusion matrix, and the layers we are going to use from Keras are convolution 2D, max pooling 2D, flat and dense inputs, global average pooling 2D, dropout, and rescaling. This is kind of important because, especially when you are working with images, when you open an image, it usually goes from 0 to 255 in integer, right? But neural networks don't run on integer, they run on float numbers, so usually you need to rescale them by dividing the image over 255. So that's basically what those divide or multiply the inputs by a number. Okay. So same as usual, maybe OpenCV. I don't think we're going to use it here, but just in case. TensorFlow, that's it. It's reported, and that's it. Okay. I'm going to take a long time to explain all this. Okay. So with this cell, we are going to import our data set. For this, we get help from the Keras utils image data set from directory. That means we have a folder, right? So basically, we put the path of the folder, so the training folder in this case, and then it has to be like I put it. Each folder includes a single class, right? Otherwise, you won't see. For example, we have two folders, normal and effective, so that means there are going to be two classes, right? Then we must specify the image size. Is going to resize the images according to the image size you are going to put here. The batch size, I suggest you try different batch size. Don't just run my code and present the results as they are, because it's not the objective. This is just a sample code, okay? So change it for some number, I don't know. Just try to see what happens if you use 40, 10, 50, I don't know, just change it. Label mode, in this case, because we have only two classes, I went for the binary. Keras works in a weird way, so therefore by default it's integer, but we go back to, again, integer doesn't work with neural networks, I don't understand why. So binary means 0 or 1, okay? It's a single label for each image. And that's it, and then we import the data set. Whenever you are going to work with big data sets, I suggest you use these helpers from Keras, because otherwise you are going to try to load all the images into your computer, which is kind of, no, you shouldn't, because you are going to, sometimes the data sets are too huge and you don't have a computer enough to load everything. So this way they get loaded as they are needed. Okay? So basically this is just a pointer to where the images are. And now we have a class name. As you can see, found 220 files belonging to two classes. And the class names are the name of the folders, of course, because we didn't say which was the name. So of course the first one is a 0 and the second one is a 1, right? It's simple. Import this same story. We also have to just make sure that it says test, right? And now we can see the training images. You can see normal defect, you can see the defect here, right? This is a black hole. It's kind of easy to observe the defects, right? So it should be easy for the computer in theory. So now this is the custom small CNN. And usually we are going to go for a sequential. That means each line is a block. This is a block, this is a block, and they connect to each other in sequential way, as it says there, right? This is the easiest model we don't, but and that's the advantage of Keras, that it's super easy to write these things. You don't need to think. So the first one must be an input, which is a image size and the number of channels. The second one is a rescaling. We multiply the input by this factor, right, to make it between 0 and 1. And we must specify input shape, I don't know why. So the CNN was like this, two convolutional layers with a ReLU activation function in a max pooling 2D, which divides the image size in half. For the convolution 2D, there are basically 4 arguments that you need to take care of. The first one is the number of filters, in this case 8. The second one is the kernel size, which can be an integer or tuple if it's not square, but this is 3 by 3, right? The padding are basically 2 options. Value, that means we don't add padding during the convolution. I think Professor already explained that, so I'm not going to go over it. And the other is same. That means the output feature map is the same as the input and size. That means there exists padding added. You don't need to calculate how much padding, you just write here same. Okay. And then finally the activation, in this case the rectifying unit, which is the most common. So it has 3 blocks, right? Then flatten, and then we have an MLP, a multilayer perceptron, which is the dense. And the dense, you can add the number of neurons and the activation function. In this case, an activation function here. And finally, the number of nodes, which is 2, right? Because you have 2 classes. And the activation softmax, that means we will have a probability as an output, right? So we need to be careful here. Now we can bring this. And you can see how the size is reducing, right? Because it doesn't have padding. To 24, then to 22, then to 20. Remember, it has no padding. Then half, 1/10, and so on and so on. And at the end, you can see the number of parameters. It's less than 1 million. It's just shy of 1 million, which is kind of small. It's extremely small. You see the size. The size of the weights is 3.63 megas. Nothing, right? Okay, so before training, you need to compile the model. So basically, compiling means you are going to set up the optimizer and of course, the learning rate and the loss function. My suggestion is always go for ADAM. It's the most common and most proven to work. Learning rates, just pick one, a small one. This is okay. Loss function, sparse categorical cross entropy. Why is that? Because of the labels, we decided to go for binary labels. So that means this is the output from the label. So it's a single number, right? And that's increased. So according to Kera's documentation, you should choose a sparse categorical cross entropy. Okay, so I'll just leave it like that. You are going to use this. It's the only thing, the difference between sparse and just categorical cross entropy is how the labels are input. It's the function is, the equation is exactly the same as cross entropy at the end of the day. Okay? So nothing is here. And now to train it, you just call the method fit. You input the dataset, the number of epochs. 5 is not enough, okay? Don't present the homework with 5, okay? Because it's not enough. And then the class weights. The class weights must be a dictionary with the first, with the key as the class and the value as the weight of each class. So in this case, I'm not using weights, but I just leave it like that so you can know where to change if you want to use it. And now we just run it. It should take less than a couple of minutes. It's extremely fast. But it takes a little bit because the internet here is kind of bad. So that's why I put only 5. See, each epoch is extremely fast. And now it's done. And now we can plot. So the training is give us back a dictionary with the training data, and we can plot the loss function by calling the history of history in the key loss, and then you can see the training. Of course, as I said, 5 is not enough; it's still going down, right? It has to convert, so don't leave it at 5. And now we can predict here. So this is great. Put attention at this. So for this, we just call the model.predict. Okay. That's it. And then we put the test dataset. Now, I have this argmax because it's a probability, right? So we need to to see which one holds the highest probability. Otherwise, we are going to have those two values for each class. Okay? And then the confusion matrix, the true labels first, and then the predicted labels, and that's it. And it has another argument that you may use, it's called normalize. And if you want percentages instead of the number of images, you just normalize equals 2. And now we have the confusion matrix. So say it hasn't trained, right? You see the diagonal is extremely bad, so because it has a learnability. So this is the confusion matrix, how you plot it, how you print it, sorry. Questions so far? A lot of information. So if you don't put the normalize equals to true, or you set it to none, because that's the other option, it's going to give you the number of images, right? 110 for each class. Okay. That's how to train from scratch. Just get a model and compile it and fit it until it converts, and that's it. Okay? Easy. Now for a pre-train, Keras has too many. We go to the Keras applications, and we can see the models. And the accuracy has exception, BGE 16, 19, ResNet, exception, mobile net, DenseNet, efficient nets, more efficient nets, Connext, which is the latest one. So you can use any of those right here. Okay? But so basically, we have to import a model with weights, okay, from ImageNet, because the weights are from ImageNet. There are no. Keras only includes the ImageNet. You cannot go for another unless you have the weights yourself. So you just call TensorFlow Keras application BGE 16. Include top files because we don't want the MLP, right?
Yeah.
I mean, it's ImageNet. You know what how many classes ImageNet has? It's 1,000 classes. And we are only trying to classify 2, so that doesn't make sense. So basically, you will just go for include top false, and we need to specify the image size. That way, we are only going to have
The top.
yes until here. Let's say until here. The top is this part, the MLB, the classifier. Okay. Where's it here? Now, how? Because this is only the feature extractor. And we don't want to train it because it's fine-tuning, right? It's pre-trained. So now we just set the model as trainable equals false, that's it. And then we can see how many parameters trainable. Now it's going to get the weights and load it. It's extremely, and you can see here if it's going to train or not, right? Trainable parameter 0, because we set it to trainable false, right? It has kind of, compared with our simple CNN, it's extremely rich, right? So now we need to add a classifier to this part, right? You see, it depends on max pooling and not a dense layer. So we need to add some classifier here. So for this, we go back to the sequential model. We input the first model there. Then we can go for something like a global average pooling, then go out and whatever, same copy from the previous one. Now we see the summary. We see now trainable parameters is much less than the previous custom CNN, right? Because it's only the MLP. To train the same, exactly the same, just compile it. But the important part for the retrain or transfer learning is this. You just have to set the thing to false. Yes, and remove the MLP and add your own MLP and train only the MLP. The idea of transfer learning is that some of the features that the ImageNet has learned can be useful for the training. So you don't need to train the filters itself. Basically, you just train the MLP. There must be some of the features has far too many. So that's the idea. I'm not going to train the BG, but I will show you the Connext. Same story, you use Connext Tiny. We are using the Tiny because it actually Connext is too huge. It's like 1 billion parameters, which I don't even know if this is capable of training. So we are going for the Connext Tiny, which is not tiny at all. you will see how huge this thing is. See, layer, 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 and layers. There's a lot of blocks and it's twice as many as the
GG16.
yes.
Double.
And now you just have to add your MLP and do the training. Okay. Questions? And that's it. And I don't suggest you going to the complex from scratch because it's hard. Yeah, I don't think it requires experience to train those big models from scratch. It's not just fit and that's it. No, it doesn't work like that. We are going to use a big neural network for the term project cohort training. So I don't think you have the patience to try experiments that much, especially if you don't have good equipment. I trained the complex tiny from scratch and it took me 10 hours. So.
We have a lot of equipment. The problem is we don't know how to use it. It's useful. We have a big CPU and it contains for the TensorFlow 100. The
Tesla 100,
yeah.
100.
Yeah.
That's 16, 64.
Yeah, it's huge CPU in our lab, but we don't know how to use it. That is the problem.